Okay, let's go ahead and get started. This is the second part of week 2 for Eltec 213, electrical fundamentals. Last time that we got together, I gave you a practical example of a DC source. The analogy I made was photovoltaic arrays that were connected in such a way that we would get 600 volts. And then I gave an example of a water pump that we were operating at a very long distance from the source. That's an impractical application because, as we showed, it would not be feasible or economically feasible to run it that way because you'd lose so much power in the lines. Okay, part of that assumed that you understood the difference between the 3 types of hookups that we encounter in our study of both DC and AC electronics. And so tonight what I'm going to do is regress a little bit. I'm going to take a step back because I know that there were some people that got it and some folks that didn't. And again, if you don't get it the first time that I present it to you, don't feel like you're not going to be able to get it. Very often when I was in school, I did not get it the first time. And a professor told me long ago that if I ever found myself in that situation, I needed to tell myself that's right where I'm supposed to be. Because if you got it the first time, you'd be number 1 at Harvard, or you'd be at some Ivy League school or something. Okay, so what I want to do tonight is I want to talk about the 3 different types of connections that we find in our study of DC electronics, and then I'm going to focus in on one of them, okay? Because we don't study all of them at the same time, but I want to show you the contrast between the 3 different types. There's what we call the series connection, and the series connection involves loads, or resistors in this case, that are just connected end to end, or they're coupled together. So if this was resistor 1 and this was resistor 2, those resistors would be said to be connected in a series configuration. Okay? I'll draw a squiggly line to separate the board here. The second type is parallel. Parallel configurations. Okay? In a parallel configuration, resistors are drawn in a configuration that's known as a back-to-back configuration. So if this were, let's say, resistor A and this were resistor B, those resistors would be said to be connected in a parallel configuration. So you can see that these are very different. In other words, the current that flows through resistor 2 has to flow through resistor 1 because it's got nowhere place else to go. Okay? But in this case right here, the current that flows through resistor A, assuming that this is hooked up to some kind of a battery or some kind of an energy source, the current that flows through this resistor right here doesn't necessarily have to be the same as the current that flows through this resistor. It depends on what the values of the resistors are. And what is resistance? Opposition to current flow. So if this has a lot of opposition to current flow and this has a lower opposition to current flow, then you would expect more of the current to flow here, less of the current to flow here. In a series configuration, it doesn't matter if this is 10 ohms and this is 1,000,000 ohms, the current is going to be the same through both of them, okay, because they don't have any place to split off. Moving over to the right a little bit, the final configuration is what we call combination circuits, and I'll just abbreviate combo. And combination circuits are basically resistors or loads that are connected in configurations that can't be defined as series or parallel. They are rather a combination of series and parallel. So if this were resistor 1, this were resistor 2, and this were resistor 3, then it would not be accurate to say resistor 1 is in series with resistor 2. Can anybody tell me why? What's the rule for determining if they're in series? The current is the same. Okay, so would it be fair to say that the current flowing through this resistor would have to be the same as the current flowing through this resistor? No. And the reason is because there is we call it a node, or a point in the circuit where the current can branch off. So the current that's entering this point or this node in the circuit can branch off. Part of it can go this way, and part of it can go this way. Okay? So we break up our study in DC electronics into 3 primary components, and that is the study of series connected resistors, the study of parallel connected resistors, and the study of combination connected resistors. Okay? We're not going to try to do all of that tonight. We're going to focus on series connected resistors because we want to have a real good handle on each one of these. The reason that I put them on the board all at once is to show you that there's more coming beyond series connected resistors. Now, if we come back to a series configuration of resistors, okay, one of the things that we always are trying to do in the study of electrical engineering or electrical technology is we're always trying to simplify things. If something is extremely complex and you can't understand it, it doesn't do anybody any good. Okay, and so we're always trying to take things that may or may not be complicated and make them simple. Okay, and so when we're presented with a circuit that has a whole bunch of resistors or loads, you know, they could be space heaters, or they could be microwave ovens, or they could be one of a million different things. If we have a number of different loads that are all connected in series, there is a formula that I'm going to show you in a moment whereby we can combine all of those resistors into one resistor that represents the effect of all those resistors acting simultaneously. Okay? You guys follow me? Okay, good. All right. So there's a generalized formula for series connected resistors, and the formula looks like this. It's in your book. It's in your notes. And by the way, for those of you that are looking at the videos and looking at the notes, the presentation on series connected resistors is actually a week ahead, okay, of what I'm doing. And there's a method to the madness. In other words, I'm trying to introduce you to it before you read it, so that when you read it, you get more out of it. I've found that that's more effective. Okay, so the formula that we use is that the total resistance of series connected resistors is equal to the algebraic sum of the individual resistors. So what does that look like in a formula? It's real simple. Okay, it's like adding dollar bills. Okay, it's whatever the value of resistor 1 is plus whatever the value of resistor 2 is plus whatever the value of resistor 3 is, and then I'm going to skip over this metallic part here, plus dot 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 the value of whatever resistor n is. Resistor n represents the last resistor or the last load that's hooked up. And so what that means is that there could be only 2 resistors, and then you would just use these first 2 terms. There could be 3 resistors, you'd add the 3 up. There could be a million resistors, and you would add them up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay? And what you would substitute in for the value of the resistors is how many ohms is associated with the resistor. What is the rating on the opposition to current flow? So for instance, if this resistor was 100 ohms and this resistor was 200 ohms, then the total resistance would simply be equal to 100 ohms plus 200 ohms for a value of 300 ohms. Okay, now let me show you how that allows you to simplify a circuit. Let's say that we had that exact circuit over here that was connected to a battery. So let's say that we had a 12-volt battery, and that 12-volt battery was connected to two resistors, the same two ones that we just had, and we called the first one resistor 1, second one resistor 2. Resistor 1 had a value of 100 ohms. Resistor 2 had a value of 200 ohms. Okay, so resistor 1 is 100 ohms. Resistor 2 is 200 ohms. Okay? Now, using this generalized formula right here, we can find out what the total effect of those two resistors in series are on the load, or on the source, and on the whole circuit. So if we used our formula, the total resistance would be equal to the sum of resistor 1 plus resistor 2. And that would simply be equal to 100 plus 200, and that obviously is all in ohms, and that would be equal to 300 ohms. Now, what that allows us to do is it allows us to redraw the circuit in a simplified form. Okay? It allows us to draw a circuit that doesn't look the same, but if we were to build the two circuits, they would act the same. In other words, they would draw the same current, they would dissipate the same power, they would have the same voltage drop. Everything about them would be the same, except that you'd have one resistor instead of two. Okay? And so the equivalent circuit to this circuit right here, using the series circuit theory, is the same battery. So we got a 12-volt battery connected up to one resistor. And that one resistor is going to be the equivalent resistor, or the total resistor, or the total resistance. And that total resistance we found to be 300 ohms. Okay? Now, obviously it simplifies it because you only have two things in the circuit, whereas in the beginning we had three things in the circuit. We had a battery and we had two resistors. In the simplified circuit, we have a battery and one resistor. Okay? The other thing that simplifies the analysis of the circuit is the fact that when we go to calculate things like how much current is this circuit drawing using Ohm's law, okay? And current is measured in the unit of what? Amps. How many amps is the circuit drawing, okay? And if we know what the voltage is, in other words, we know what E is, and sometimes that's called V in some books. In our book, it's called E. And we know what the total resistance is, but we're looking to find the current, then we want to look at our Ohm's law formula wheel for a formula that says current is equal to something in terms of E and R. So what would that formula be if you look in your book?
E over R.
E over R. So the Ohm's law formula wheel tells us that current is equal to the ratio of voltage divided by opposition to current flow, or voltage divided by resistance. So if we simply plug the numbers in, we get 12 volts divided by 300 ohms. That's the opposition to current flow. And then when we do that calculation, if you get your calculators out, for those of you that have them with you, what do you get when you take 12 and you divide it into 300? 0.04. So this is equal to 0.04 amps. Now, because of the fact that you need to know how to make conversions in the metric system, okay, if, let's say, you were given an exam, an aptitude exam for a company, and they gave you this exact problem, but it was a multiple choice problem, and the only choices that you had were in milliamps, then what you would have to do is convert that number of amps, 0.04, into milliamps. And how would you do that? Right, you would multiply it by 1,000. There's another method, if that's not apparent to you, that we call dimensional analysis, where you can multiply it so that the units cancel out. In other words, if you take that number and you multiply it by a fraction, then you can get the units to go from what you have to what you want. And it's always, 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 always done the same way. Okay? Whatever the unit is that you're starting with, that's the same unit that you write in the denominator of your conversion factor. So we would write amps here. The reason is because anything over itself cancels out, becomes 1. And that's how we get rid of amps. Because we don't want amps, because amps is not one of the answers. Okay? We want to convert it to milliamps, because that's one of the multiple choice options on our exam. Okay? And we know from either our cheater sheet or from memory or the book, okay, that for every 1 amp, there's how many milliamps? There's 1,000. There's 1,000 milliamps. So when you look at the dimensions, the amps cancel out, and you're left with milliamps. So when you do that conversion, the current is equal to how many milliamps? 40. So 0.04 amps is the same thing as 40 milliamps when you convert it into the metric system. Now, the shortcut way to do it is to just count decimals. If you're converting by a multiplication factor of 1,000, you're going to move the decimal over 1, 2, 3 places. Okay, and since there's nothing there, you have to put a 0. So your decimal point is actually there. Okay, so both answers are correct. It's just a matter of what you're being asked to find. Are you being asked to find amps, or are you being asked to find milliamps? So when we come back to our equivalent circuit, we have the current equal to 40 milliamps flowing in the circuit. Okay? Now, if we go back to the original circuit that we started with before we simplified the circuit, and we wanted to represent the current that was flowing in that circuit, what would the difference be between the current that's flowing in the equivalent circuit and the current that's flowing in the original circuit that we started with? No difference. The current here would also be equal to 40 milliamps, and that's why these guys are called equivalent circuits. Those are equivalent circuits. And that's what this symbol right here designates. They're interchangeable with each other. Okay? In other words, they're not physically the same, because this one has 2 resistors and this one has 1, but they are electrically the same, okay? Because all of the electrical properties are the same between the two circuits. With a slightly more complicated series circuits are not difficult. The reason they're not difficult is because all you're doing to simplify them is just adding algebraically. You're taking the numbers in ohms of the loads and you're just adding them up, okay? When we get into parallel circuits, the formula gets a little bit more complicated, but it's not hard. It's not hard if you have a calculator and know how to use it. And then the combination circuits, still just a little bit harder, but again, turns out to be something that you can simplify down into just one resistor, and that's what our goal is. So let's take a look at another example where we have more than 3 resistors that are all connected in series, and see that the same approach works. Let's say that we have a DC source, and the DC source is rated at 50 volts. Okay? So that's our source voltage. It's equal to 50 volts. Okay? And connected up to the DC source, we have 1 resistor, 2 resistors, 3 resistors, 4 resistors, 5 resistors. And then it loops back as a return path to the DC source. Now remember, these resistors all represent loads, and they could be anything from a microwave oven to a toaster to a space heater to anything that you can imagine, okay? So we're going to label these loads as resistor 1, resistor 2, resistor 3, resistor 4, and resistor number 5. Okay? Now, using the same exact approach that we used before, we are going to find out what the equivalent circuit would be to the circuit that we're given. Now remember, the equivalent circuit is, in the case of resistors, always going to be one load. It's possible you could have more than one source, and you can combine those two, and we'll show you how to do that at a later time. Okay, but an equivalent circuit in its simplest form is one source, one load. And that makes it easy, because then you can just use Ohm's law, and it's a simple problem. Okay? So for this problem right here, and I'll move over to this board so I don't run out of room, the total resistance is simply going to be equal to the sum, the algebraic sum, and I differentiate between algebraic and vectorial sum because when we get into AC, we'll study something called vectors, which I'll explain at that time. Algebraic just means you add them up like you add money. Okay? There's no direction associated with it. So the total resistance is going to be resistor 1 plus resistor 2 plus resistor 3 plus resistor 4 plus resistor 5. And then if we had more resistors, we would just add them in the same way. In this case, we only have 5 resistors, okay, and so we stop at resistor 5, okay? Now, assuming that, let's just say this resistor was 10 ohms, this resistor was 20 ohms, this resistor was 30 ohms, this resistor was 100 ohms, and this resistor was 400 ohms, okay? Then we would be able to, in the end, find an equivalent circuit that would have one battery and one single resistor that would represent this circuit right here. Again, they're not physically the same, but they are electrically the same. And that's the reason that we always want to go to the simplest form, because it makes our lives easier in analyzing the circuit. The voltage doesn't change. This is still 50 volts. The total resistance that we have in the circuit, we have to calculate. So resistor 1 was 10 ohms. I'll save the unit until the end. Resistor 2 was 20 ohms. Resistor 3 was 30 ohms. Resistor 4 was 100 ohms. And resistor 5 was 400 ohms. And anytime I put brackets around the whole thing, and then I put a unit at the end, it means the unit applies to everything in the brackets. It's called the distributive property in algebra. Okay? Okay, so what is this? 400, 500, 530, 560, 560 total. 550 with the 20, 560 with the 10. Okay? So the total resistance is equal to 560 ohms. Okay? Now, that circuit over there looks a whole lot simpler than this circuit over here, doesn't it? Okay? And when we go to analyze things in the circuit, like let's say that we needed to figure out how much current was flowing in the circuit and how much power was being dissipated by the load. Okay? Then if we wanted to figure out the current that was flowing in the circuit, we would use the same formula that we used last time, right? Current in the Ohm's law wheel is equal to voltage divided by resistance. And in our case, that's 50 volts divided by 560 ohms. So what do you get when you pull your calculator out and plug those numbers in? 0.09 amps. Now, can anybody look at that and tell me how many milliamps that would be? 90. And if you needed to, you could use dimensional analysis to cancel the units out. But probably by now, you're able to count the decimal places. Okay, we're counting 3 decimal places. 1, 2, and then we have to add a 0. So we get 90 milliamps.
Do you want these like to the nearest milliamp? Because the nearest milliamp would be like...
No. Yeah, we're not. The significant digits that we're dealing with for this analysis, we're rounding up, okay, to the nearest hundredth, okay? So 10th, 100th, rounding up to 0.9, okay? And then if we wanted to calculate what the power dissipation was, both in the resistor or the load, let's say it's a toaster. Okay, we want to know how many watts is the toaster consuming. Okay? That would also be equal to how many watts the battery was generating. Because the watts have to come from somewhere. And there's only 2 things in the equivalent circuit. There's the thing that produces the power, we call that the active source, right? And then we call this the passive load. This is just sitting there waiting to heat up, okay? So if we want to find the power that's being dissipated in the load, and we know, let's not use current, let's use voltage and resistance since we have even numbers. What is power? What is the formula for power if you know voltage and resistance in the Ohm's law formula wheel? It's voltage squared divided by opposition to current flow, or R. Okay, so when we plug those numbers in, we get 50 quantity squared divided by 560. This is ohms, this is volts. So So what do you get when you take 50, you square it, and you divide it by 560? 4.46? Okay. So that's 4.46 watts. Now, the reason that that's an important number is because let's just say that you're designing toasters. Okay? And toasters generally consume a lot more energy than that. But, you know, this is just an example of how you would do it no matter what the numbers were. Okay? Let's say you're designing a toaster and you have to pick out filaments that you're going to put in the toaster. Anybody that's ever toasted bread and looked down in the toaster, you see the little filaments get red hot and they heat up, and then that's what toasts the bread, right? So if you're selecting the filaments and you're going to order a train load of filaments to build, you know, 10,000 toasters, okay, you're going to have to specify the diameter of the filament and also the energy rating of the filament, okay? And so this number is going to be a very important number to you, okay, if you had a toaster that had 1, 2, 3, 4, 5 elements in it. Because the sum of all of those toaster elements would be equal to an opposition to current flow of 560 ohms and would dissipate that much energy. So you would have to be sure that each individual element wouldn't be overloaded and the toaster as a whole wouldn't be overloaded. Okay? So this is real world application. You know, I mean, if you're working for a company that makes toasters, you know, you're definitely going to have to understand this, you're going to have to know it, and you're probably going to have to explain it to somebody before they sign the check for a train load of toaster elements, you know, the filaments that go in the toaster, you know, to spend, you know, $50,000 or whatever. You're going to have to convince them that you've done your homework and that the filaments that they're purchasing are not going to burn out and they're going to have a bunch of toasters recalled. Okay? Now, what I want to do is I'll go ahead and erase this. I'd like everybody to get out a piece of paper and a pencil and a calculator if you have it. And what I'd like you to do is I would like you to, this is going to be a check for understanding. Okay? What I would like you to do is to consider the following circuit. You've got a DC source that's rated at 60 volts. You have got 4 resistors. Resistor 1, resistor 2, resistor 3, and resistor 4. Okay? R1, R2, R3, R4. R1 is 12 ohms. R2 is 17 ohms. R3 is 14 ohms. And R4 is 10 ohms. What I would like you to do is I would like you to figure out what the equivalent circuit looks like. In other words, if we were to reduce this to one battery and one resistor, and then I would like you to calculate what the current is that would be flowing in both the original circuit and the equivalent circuit, as well as what the total heat dissipation would be in the load, or what the watts, the power that the source would have to deliver to the loads in order for the circuit to operate properly. So what I'm going to do, since we already know what the form of the equivalent circuit is going to look like, I'm going to draw that on the board because that's no mystery. We're going to have one battery and we're going to have one resistor, and the battery is going to have a voltage of 60 volts DC. Of course, this is all DC. And this is going to be our total. That's our total equivalent resistance. So first of all, what is our total equivalent resistance? 53? Does everybody agree with that? 53 ohms. So this circuit and this circuit are electrically equivalent to each other. Okay? What about the current? How much current is flowing in this circuit right here? 1.13 amps. And did we get that from the formula current is equal to voltage divided by resistance? Okay? And I assume that you put in 60 volts for the voltage and you put in 53 ohms for the resistance. And that was where you got the 1.13 amps. And then how about the power that has to be generated by the battery to run this load? 67.92 watts. 67.92 watts. That's what we're getting. Power is equal to 67.8 watts. Okay? And let's check that. So the formula that you used was what? Power is equal to voltage times current. And that was equal to 60 volts times the current, which was 1.13, right? Amps. And that was approximately 67.8. Okay? So for anybody that wants to do extra problems or is viewing this recording, what I suggest that you do is I suggest that you look in your textbook, find an example problem, take the numbers out of the problem, close the book, write the problem down on a sheet of paper, and then see if you can come up with the same solution that the author did. If you get stuck midway, you can peek. But obviously you want to be able to do this on your own, without looking, because when you have your midterm and your final exam and ultimately your aptitude exam for employment, you're not going to have the luxury of being able to peek. Okay? So this really is all there is to combining circuits that have series connected loads. Are there any questions? Sir?
On a test, would you give us the formulas, or we have to memorize?
On a test, would I give you the formulas? Okay. For my course, and this is not necessarily the case for aptitude exams in industry, but in my course, I allow you to have 2 8.5 by 11 crib sheets. Okay? And so what I would do if it were me is I would probably write down series, and I would put R total equals R1 plus R2 plus ... Rn, telling me that I just add them all up. Then what I would probably do is I would probably put a short example problem underneath it. And that way, if you're given a problem and it's like this one, and you completely draw a blank, sometimes you do that on exams, you completely draw a blank, then you can look to your crib sheet and you can say, oh, wait a second. For series circuits, all I do is I just add the resistors up, And then here's an example problem that I put right below it. And then that'll refresh your memory. And then you'll come over to this and you'll go, oh, that's right. I'm taking this circuit, which has a whole bunch of loads in it, and I'm converting it to a circuit that has only one load in it. Right? And then you could do that. And then, of course, you would also have your Ohm's Law formula wheel, which I suggest you put on your crib sheet. I don't want there to be surprises for you. I don't want you to have to memorize everything in the class. I want you to, basically come to a decision about, what you don't need to write down on the formula sheet, like maybe that an electron has a negative charge. Maybe you don't need to write that on your formula sheet because you just know it, okay? So you don't take up the space. But for solving circuits that are series circuits, maybe you don't have enough practice yet so that it's natural enough to you as the charge on an electron. And so you would then, put that formula on your sheet. And then when we get to parallel circuits, same thing. And then you put an example problem. And then combination circuits, same thing. And that way, no matter which problem you get, you can go to your crib sheet and you can see an example problem and you can work it out. Because in the real world, when you start working in industry, you're going to have access to resource material. And that's just the way it is. Okay? Nobody expects you to memorize everything. And the kinds of questions that typically you're going to get on aptitude exams are going to be questions that you don't even need a calculator for. Most aptitude exams don't allow you to bring a calculator. Some do, but most don't. Because, nowadays you can put so much into a calculator because they're programmable. You can put text in there, and you could put pages and pages and pages of information in there. And some of them you could scan them and then just the USB cable just feed it into the thing, and basically have like a mini book sitting in front of you. And they don't want that. They want to know, do you understand that in a series circuit you just go this plus this plus this plus this plus this is this, or whatever. Okay? That's a great question. Any other questions? Okay. If we have no other questions, then we will dismiss for the evening. If you have anything that you need to talk to me about individually, come on up and we can do that up here.